Hello again, this is Marcelo, and today I'm going to be doing the next problem in the Project Euler set of problems. Today it's about the Fibonacci sequence. If you don't know what the Fibonacci sequence is, it's just a sequence that generates numbers by adding the previous two terms. So if it starts at 1 and 2, and then it adds them both up, and it becomes 3, and then 2 plus 3 becomes 5, and then 3 plus 5 becomes 8, and then so on. And we want all the values that do not exceed 4 million to find the sum of the even value terms. So if we want to check here, I'm going to be doing this again in Python. You can do it in whatever programming language you want that supports simple mathematical operations. What you want is a simple function that for the first term it returns 1, for the second term it's going to return 1 as well, and then for all terms after that it should return the sum of the previous term with the term before that one. So you can kind of just create a quick function here that does exactly this. So we check of n, and then what we do is we check if n is below 2. So if it is, we just return 1. Otherwise, we return the next term in the sequence, which is f of n minus 1 plus f of n minus 2. And this should be pretty simple enough to check. So if we just print here the result of the first value after 2, we can see that it is number 2 in fact. And then if you check the one after that, it should be 2 plus 1, which equals 3. And if you check the one after that, it should be 2 plus 3, which equals 5. So this works, but we don't want just this value, we want the sum. So let's initialize a value at 0. And we want the sum of all Fibonacci numbers below 1 million. So we just check if it's below a certain limit. And if that number is, if the current number is even, so if it's divisible by 2, we just add it up. And to calculate this number, we're just going to call Fibonacci of 1. And we can start here with an index value of 1 and use that instead. And once you check if it's even, then we just increase that index value and calculate the next iteration. So this should work. So if we start with a limit of 0, it should probably output 0 because there are no even numbers. Now, if we go at, for instance, 5, the only even number is 2, so it should print 5. So if we check 5 here, this works at 2, and if you check 10, then it should be 2 and 8, which should equals 10. So it looks like it works. If we check for 100, it should be, if we check the sequence here, 2 plus 8 plus 34 equals 44. And looks like it works pretty well. So if we change it to the target number, which is 4 million, should work, but it's super slow. And the reason for this is because it's a recursive function that it's calling itself several times over, and it's kind of doing duplicated work, especially because when we check for Fibonacci of n, and that means we check for Fibonacci of n minus 1, we check for Fibonacci of n minus 1, it means we're going to check for Fibonacci of n minus 2 for the second time. And this is just kind of useless work. There are many ways we can improve this. An easy way to improve this is memoization. And the idea behind memoization is just that we would keep an object with the saved values. And if f of n minus 1 or f of n minus 2 has been calculated, we just get it from there. So it would make it much quicker, but there is easier way to do this. You can just iterate naturally through the sequence. So instead of calling f Fibonacci here, we can just start instead with the values of 1 for the first two numbers, and we'll just delete the whole thing here. And then we'll be checking the second value instead. And the idea here is that after checking the value, we update them to be so that the first value equals the second value, and the second value equals the sum of them both. So we don't need this anymore. And if we check here for 100, the answer should again be 44. Looks like it works. We undo it and check it for 4 million again. Now this is much faster, but there are still some improvements we can do. So if we check the sequence of Fibonacci, we can see that the first numbers are odd, and then the numbers after that, the third number is even, and that repeats itself. Interestingly enough, that it's easy to see that the two numbers after the third one are odd, and then the third one after that is even. So every third number in the Fibonacci sequence is even. So instead of calculating and then doing this check, we can actually remove this check by just storing always the third number. The way we do this is by just utilizing the third number instead. And here we can just add the third number, and instead of doing this calculation, what we do is we iterate by using a equals the third number plus the previous one, and then the b would equal the third number plus its new value, so the fourth number plus the third number, and then the third number would be the fourth plus the fifth number, so the updated values of a and b. And this again should work. So if we check for 100 first, just to make sure that it works for low numbers, it works again. If we check for 4 million, we got the answer again. Pretty simple. But there is an interesting property here. We can actually try and guess a little formula for infer formula for Fibonacci numbers. So if you go again to the numbers, we know that each number is the sum of its predecessors, but these two numbers are also the sum of its predecessors. So we can kind of try and figure something out here between this formula. So if f of n equals f of n minus 1 plus f of n minus 2, then we can see that f of n, we can replace this f of n minus 2 with f of n minus 2 plus f of n minus 3. And since this is being counted twice, so we're going to include here f of n minus 2, you can actually see that it's just the second one here, and this is the equivalent formula. So you can replace this again with 2 that multiplies f of n minus 3 plus f of n minus 4 and f of n minus 3 again. So if we continue to iterate over this, that's missing a parenthesis here, we get that f of n equals 3 times f of n minus 3, this can be maintained here, plus 2 times f of n minus 4. And we can go further here by replacing the 2 f of n minus 4. So we maintain the f of n minus 3, which is 3 times f of n minus 3 plus 2 times f of n minus 4. And this is equal to f of n minus 4 plus f of n minus 4. And you can just replace this instead with f of n minus 6, minus 5, plus f of n minus 6. And we can replace 3 of f of n minus 3 here with, let's see this, f of n minus 4 plus f of n minus 5. And so what this means is that if we check this, this actually is simply f of n minus 3, and this would give us f of n is 4 times f of n minus 3 plus f of n minus 6. And since we know from this formula here that every third number in the Fibonacci sequence is even, we know that both of these are even. So we could actually just do a separate function for even Fibonacci, that something like we could just say that the first one is 2, so that's the first value in the sequence. The second one is 8, and the ones after that are the nth number would be 4 times the previous one, which is n minus 1, plus the one before that. So it just kind of we can kind of transform the sequence here, and instead of keeping 3 numbers, we would just get, so the first one would be 2, the second one would be 8. We can now get rid of the third one, and we can always just check the second one. And we know that it's always even, so we always just add it. And then when we update it, we would just do that A would equal the next one, and B would equal that same number. We can just delete this as well. B would equal 4 times A plus B. And let's just delete this whole draft here. I know this may have been a little bit confusing, but if we check now, for instance, 10, they should still remain our 10, but this is like the very edge case, so this is actually not working. The reason is because it's not properly calculating. We should actually start the sum at 2, since since it's already included here. So these ones are okay, and then if you add it to 100, then it should be again 2 plus 8 plus 34, 74. So this is wrong now. And what is wrong here is perhaps the way that this is being calculated. So this is not doing well. And how can we fix this? The reason here is that s plus 2 equals 5, but B here we will always be jumping. B here is probably going to be above 100 by the time we calculate the next one. So yeah, this adds up. This forgets to add up from the 44 one. So what we can actually do here is just move the sum to the end, so that it does so after calculating the value. And here we kind of already have to start with 10 for both numbers having already been added. And why this still doesn't work, let's see. The idea here is, oh, it's because this is actually inverted. So if we do something like this, it should actually be the sum of the current one plus the previous one. So now 10 is okay. For 100, it should be 44. And then for 4 million, it should be 46. So nice. Pretty simple algorithm. Gets a little bit confusing with the formula for even Fibonacci numbers. Once again, now if we go here to HackerRank, they have that similar thing. And the idea here is that it's the same problem, but instead of 4 million, it always gives us a different output. It always gives us a different input and expects a similar output, since there's already numbers we can calculate. So we can kind of use the same thing here again. And the idea here is just to reutilize the function here, so you can kind of do a fib sum for n here, and just use this as the limit instead of our 4 million limit here. And if we just indent so that everything is in proper place, and for each n we just called fib sum. If we just run the code, let's see if this works. This looks like it works. If we submit it, has about 5 test cases. These are still a little bit slow, and we can improve this by simply memoizing. So the idea here is that since we calculate each value, in this case progressively, when we calculate the answer for 10, it still includes 10. If we calculate it for 100, it still includes 10, but it's not necessary. But if we had calculated 100 before 10, then we would already have the answer for 10 calculated at some point. We wouldn't need to do it at the same time. So it might be useful to memorize the value here of this of the sum, because it might have already been calculated before. But otherwise, this works pretty well. All test cases passes, and thank you. If you like this, let me know. If you have any suggestions, any interesting problems you might get to work on, I would love to know some. Subscribe. I'll be continuing to be doing videos like this, and see you in the next one.